All right, welcome back everyone to another round of Astronomy on Tap State College chapter. My name is Michael Roderick, and together with Jacob Lund and Arvind Gupta, we run Astronomy on Tap here in State College. So thank you all for coming out again. We have a great night tonight. We're going to be talking about astrochemistry, yes, how we do chemistry in astronomy, as well as looking for aliens, which I feel has become a common theme for our recent talks, but I am okay with that. So, the way this works, we're going to have a quick make your own astronomy cocktail lesson with Jacob. Then we're going to get started with our first talk with Dr. Andrew Burkhardt. Then we're going to go for trivia with Arvind, astronomy in the news with Jacob, and then back for our second talk with Steve Kerby, and then we'll find out our trivia answers and our winner. So I'm going to go ahead and get this started and hand off to Jacob and show us what you are making.
All right, so hopefully everybody's in the holiday spirit. That was sort of the inspiration for our drink this month. You can see that I'm certainly in my holiday spirit, got the socks, got the PJs, feeling the Christmas spirit. So what we're making this month is a star and galaxy beer nog or eggnog with some beer in it. So it fits all of our check boxes for being holiday themed and have a little bit of a beer cocktail going on. So hopefully you saw the ingredients. If you're doing it as I will be, making the eggnog from scratch, be warned of a few things. This does contain raw eggs, so you should be using pasteurized eggs. But if you just got regular eggnog and you're just going to be adding to it, you can just watch me make eggnog and maybe not fail. This will be the second time making it, having made it once for the picture that you saw in those preview slides. So what we'll need is a fun star anise hole. I can't actually see my own video, so hopefully you can see this. This is a nice little star anise, a fun little cinnamon stick for garnish at the end, some nutmeg. You'll need a whole egg that's I've already split into the yolk and the egg white. You'll need some heavy cream and some milk. Again, I've already measured these. You saw the measurements there. It's 1 egg. This is 2 ounces of cream and 3 ounces of milk, and then 2 tablespoons of sugar. So if you're making it at home, you'll also need your nice hand mixer. So let's go ahead and get started here. If you have your regular eggnog, just hold off for just a little bit. You'll have to watch me. So here we've got our egg yolk. We're gonna take our egg yolk, pour it in. We get all of it here. I accidentally broke the yolk, so forgive me. And we're going to take the sugar, and then we're just going to beat those two together until it forms a nice smooth consistency. So apologies if this is loud. Maybe move this right here. Michael, fix my audio if it's too loud.
I think I said at one point during one of these shows that this really felt like a segment of Live with Regis and Kelly, and now even more so with our live on the air eggnog making.
Yes, so we have a smooth consistency here now. Hopefully it's all smooth. Hopefully I got all the edges. If not, there'll be maybe a few little granules of sugar. So that's good. Next, what we're going to do is to this, we will add our milk, our cream, and our bourbon that we have just a splash. I think you want just a little less than a teaspoon, so not that much if you're making one. If you're making multiple batches, which Michael, I think, did post the full recipe, which makes a batch of 4 to the YouTube comments as well. So there's that. You'll want a little more, but for this, we just want a little splash. And actually, we're going to start with the milk. So stir in the milk. stir in the cream. You should have something that's still pretty runny, but a little thicker, kind of a creamy off-white color. Also, this is, I've only had eggnog that I can recall once in my life, and that was earlier this week. So I don't actually know how this compares to a store-bought eggnog. So fair warning there. And now we're going to add just our splash of bourbon. I'm just going to pour it in here to make sure that we just get a little bit. You don't want to go too heavy on this. Don't want it to be too strongly bourbony. Unless you do, there's really no wrong amount. I think I prefer a softer flavor. Okay, so we've got that in there. Go ahead and give that a little stir. And then we're also going to add in our dashes of nutmeg. So this is ground nutmeg. I kind of like the nutmeg, so I'm going to do, I guess, four dashes is what I did. That looked about right. Maybe too much, but do what you feel comfortable with. All right. Next, what we're going to do is we're going to do a little more beating. So apologies for the noise again. And we're going to beat our egg whites until we get stiff peaks. So this will take a little bit of time. Switch my cord.
If you did happen to just join us during this part, this is Astronomy on Tap. We are just currently making our drink. We will be getting to the talk shortly. Don't worry. You are at the right place.
Turbo mode.
Well, those look like some fairly stiff peaks. We're going to call that good because I think you guys are tired of listening to that. All right. So now what we do is we carefully kind of fold in our stiff peaked egg whites into the rest of the mixture. To be honest, I'm not really sure the best way to fold. I kind of don't really enjoy mixing all that well. So I'm just kind of doing this and saying that's good. Now there are various ways of making eggnogs. This is using the egg white stiff peaks, kind of gives it a frothier mixture. You can do other things and kind of basically make almost a custardy kind of thing by heating the egg yolks. This also cooks them and slowly heating them up, not too much or else you'll get curdled eggs. and then you chill that again. But okay, this looks pretty good. So basically what I have now is the eggnog. So if you bought your own, that's the step I'm at. Hopefully maybe you've added your bourbon to it. And yeah, so now what we're gonna do is kind of just the final finishing touches. We're gonna take some Guinness, and we want just about an ounce of Guinness. So really not too much. Kind of the alcohol here isn't too strong, just a little bit of bourbon and a little bit of beer, but you'll have some beer left over too that you can sip on for the rest of the talk. And then what I'm gonna do is I'm just gonna take this, and it should be about the size of this cup, but I think it'll be a little bit less, and pour that on in, kind of right up to the top. Look at that. Look at that. It's beautiful. Okay, now comes the tricky part that probably won't work too well. So I've made a little galaxy stencil. I don't know how well you can see it, but a little galaxy stencil. I'm just gonna plop this right on, and then I'm just gonna sprinkle some nutmeg over top to give it a nice little galaxy galaxy swirl. Ooh, that might have been too much. Oh, that's not too bad. Not too bad. I don't know. Maybe we can take you in for a closer look. And now we garnish with our star anise. For the star in our star and galaxy swirl, put on our little cinnamon stick. Bloop. And there is our star and galaxy, longer than normal, Astronomy on Tap space themed drink. Cheers to the holidays.
Cheers. Thank you, Jacob.
Man, that's a nice swirl.
Guinness does go very well with that. I do like the cream. All right.
That's tasty.
Well, that being said, I think we are ready to go ahead and get started with our talks for the night. So as I mentioned before, our first talk is going to be Dr. Andrew Burkhardt, who's going to be talking about astrochemistry. So Andrew, go ahead, take it away. Tell us everything that you know about astrochemistry.
All right, great. Thank you. Let me just quickly share my screen here. All right, can you see that fine?
Yep.
All right, great. All right, everyone. Thanks for coming tonight. Tonight, I will be talking about some research efforts of me and my collaborators as part of the Gotham survey, to hunt for lost rings and chains in space. So obviously, this is our group logo, which was wonderfully made by one of the data analysts who had a rather over at the National Radio Astronomy Observatory, with actual spectral data shown there as the peaks of Gotham. These are my group members. I'd be remiss not to say that this is definitely a group effort here for everything that I'll be talking about today. So they mentioned, you know, what I work on is astrochemistry, and so what does that actually mean? Well, in the broad sense, what that means is the astrochemistry is basically figuring out how did we go from atoms and the ashes of stars to form things such as planets and life. So this is kind of a picture here of the stellar life cycle. So if you have some sort of star, as it ages, it'll fuse materials in its core, and at some point the star will die. It'll explode, or in some way eject its material out into the interstellar medium, which gets dispersed throughout the galaxy. It'll recollapse and form new stars. And so throughout this process, some questions that we kind of arise from this, and how we go to answer this question is the Earth's chemistry unique in the universe? And similarly, where did Earth's chemistry come from? So kind of one big question is, for example, a lot of the complex chemistry we see here on the planet, you know, both things like life, but also, you know, the rocky body we stand on. The question is what sort of chemical processes actually led to that? And so, you know, there's been these thoughts of perhaps cometary impacts, maybe bringing material in that was formed in the early solar system, that may have been the precursors to things like life, or even just different elemental components. So this is kind of what astrochemistry aims to solve, is how do we go from when those stars eject that new atomic material. So this atomic material is formed when you, as I mentioned, in the cores of stars, different elements are fused and formed into larger elements until eventually it gets to the point where it gets too massive for the star to actually support itself, at which point it explodes. This is a nice periodic table here of, instead of commonly they'll be colored by, whether they're by terrestrial things such as like, how, if it's a transition metal, this is colorized by where they're formed in the universe. So you can see a lot of them are formed, some of them are formed in the Big Bang, mainly just hydrogen and helium, a little bit of lithium, but most of the other ones are formed through the death of different types of stars. And so as these stars explode, they disperse their material throughout the interstellar medium with all these new atomic species. Even to the point where, as I mentioned, these cometary impacts, and here's a wonderful video from the Rosetta mission where we're actually looking here at a video on the surface of a comet, which is still one of the coolest things I've ever seen in my life. So I have to show it in every single slide I ever show, where in these cometary in the coma of the comets, but also on the surface, we see things such as amino acids, which are kind of the building blocks of life. We see complex molecules that, if you would have asked 100 years ago, no one would have thought they would have been possible to form out in space, but they're readily there. And the comets are kind of they're like time capsules of the early solar system. They're thought to be made out of the same material that the early solar system was. And so the fact that we see all this rich chemistry in comets makes us think that the chemistry occurred before maybe even the Earth was formed, which is pretty interesting. So the question is, how do we study the interstellar medium? Well, it would be nice if you talk to a chemist, they would love to be able to, grab a scoop of whatever they're looking at and actually study it. But unfortunately, this stuff is just way too far away for direct measurement. And so the only thing we really have to study this is the light that the molecules that we care about emit, be it as they spin, they may emit a tiny amount of light as they speed up or slow down, or as they vibrate. That's another way. Or potentially as the electrons move up and down in different states, that can also produce different types of light that produce a unique fingerprint for each individual molecule. And over the years, over the past, I would say like 50 or 60 years, we've gotten pretty good at finding new molecules. Here is a semi-out-of-date list of, as of 2018, every molecule we have found in space. As you can see, there's a lot of small atoms, 1, 2, 3, 4 atoms typically. But you can see they go all the way up. You see on the far end of it, there's these molecules such as C60 and C60 plus and C70, and even this big weird molecule, which has a little c, which means cyclic, C6H5CN, which is where I'll kind of start my story here today of what we'll be talking about. For me to talk about that specific molecule, I need to talk about this concept of aromaticity and aromatics. And so what does that mean? Well, aromatics is a special type of property that certain molecules can have. Here's the classic one called benzene, and for the chemistry fans throughout the years may enjoy all the different forms, I decided to put it up here. But basically, this is a way that carbons and hydrogens can arrange themselves such that they form a flat plane and form this hexagon of carbon with hydrogens around the center. And in these for this type of molecule, they're particularly important for a wide variety of reasons. Kind of from terrestrial, you'll hear a lot of talk about benzene and different aromatics when you talk about crude oil or gasoline, fossil fuels. There are cyclic and aromatic molecules, these kind of ringed molecules that I'll be mentioning throughout. These are found in nucleotides when you're talking about DNA and RNA. About 80% of all known molecules, if you look at Giant Catalog, have some sort of 5 or 6 membered ring in them. So they're important on terrestrial, but they're especially important also in space for this type of molecule, not just aromatics, but polycyclic aromatic hydrocarbons. Now, what's all that unnecessary wordage there? So hydrocarbons, that just means it's made out of carbon and hydrogen. Aromatics, I just kind of discussed. And polycyclic just means that they're multiple rings. So what's nice about these rings here is that they're very, very stable to chemistry or anything from wanting to destroy them. They're very, very stable. And so when you're in a harsh interstellar environment, they can last a long time despite a lot of other things happening around them. And what's nice is you can also click them together kind of like Lego pieces and form these really complex, large, multi-ringed molecules that end up being very important for the interstellar medium. There's these unidentified interstellar bands in the infrared, which are basically bright features that, as far as we can tell, seem to be associated with different types of these PAHs, as they're referred to. As they vibrate back and forth, they give off a very unique signature. And basically anywhere we look, from regions where stars are forming to diffuse clouds to where the deaths of stars are occurring to even other galaxies, no matter kind of where we look, we see this type of emission. And as far as we can tell, we believe that they come from these PAHs, although it's a little difficult to tell because, as you can see in this figure on the left, this is just some spectra. What they actually say is not too important, but you can see there's no individual molecules named there. All we can do with this sort of spectra is identify what types of molecules are there. So molecules that have a carbon and a carbon next to them. And that's just the nature of infrared spectroscopy, which I won't get into here. But needless to say, they're important in interstellar chemistry, and we think that somewhere between 10 and 25% of all carbon in space is locked up into these PAHs. So they're very, very important. But one big question, and even furthermore, they're also important as you can take these kind of small PAHs, and if you keep linking them together, you can form things such as interstellar dust. And these dust particles can coagulate and eventually form things like planets and meteorites and all the kind of rocky bodies that we're used to looking at in the solar system today. So there's a lot of different uses for these types of molecules, but it's not quite sure how we actually make them. So, and the reason that there's kind of that uncertainty is, so if you kind of look from small molecules and you build up to these very large PAHs that we're talking about, the smallest ones, as I showed on that chart, 2 to 3 atom molecules have been known for many, many decades, and we find them very easily. As they rotate, they give off very unique spectra that are very bright, and we have known about them for a while. So those are very well constrained. And for these PAHs, we're pretty sure we know a lot about them because of this infrared emission that I talked about earlier. However, this benzene molecule, which is a single ring, is near invisible. And for a number of reasons are only really visible with very special space-based telescopes, such as none that are in the air currently, but the James Webb Space Telescope in the future might be. And so why is that? To kind of briefly go over it, so benzene in particular is a very symmetric molecule in that if I take a benzene molecule and I rotate it a little bit, it looks the same every time I try to spin it. And that's very important when I'm trying to detect emission that comes from a molecule spinning. If it's a highly molecule that's very, very symmetric, it won't actually give off much emission in that sort of spectral regime, which is how we detect the vast majority of the 200 molecules or so we know about. However, if we found a molecule that had some sort of strong asymmetry that seems to be similar to benzene, that we can use that as a proxy to say, okay, if we know that this other molecule is somewhere, then probably benzene is there too. And that allows us to study the chemistry in that area and understand how does benzene form and how is benzene destroyed and how does that make larger and larger aromatic molecules. And so knowing this sort of molecule would be really important and for us to know. So as part of this, me and my collaborators looked towards a source called the Torus Molecular Cloud 1, or TMC1 for short. This picture was taken by a collaborator, Brett McGuire, and it's this little blue circled region here on the image. And here, this source is particularly useful because it's a cold, dense, dark cloud. So this is before really any stars or protostars are turning on. It's kind of just a dark cloud, which is very nice for when we're trying to detect molecules that may be very difficult to find. A lot of these properties make it quite advantageous for us. And in particular, it has a very rich this source in particular is known to have a very rich carbon chemistry. So they're known for having molecules that have lots and lots and lots of long carbon chains. And so if lots of species that contain many, many carbons around, maybe these aromatic molecules such as benzene or benzonitrile may exist. And so we use the Green Bank Telescope, which is a telescope in West Virginia. It is approximately a little bit more than 100 meters in diameter. To give you a sense of scale on there, the kind of vertical structure you see at an angle on the right side of that telescope, that's a stairwell going up, back and forth. So it looks way smaller than it actually is. It's the largest steerable object on land. The only thing bigger that we can physically steer are aircraft carriers and oil tankers. So it is quite a feat of engineering in one of my favorite telescopes, and it's in Green Bank, West Virginia, which is this radio quiet zone where you're not allowed to have a cell phone anywhere near it. Otherwise, they chase you down with a truck, which is fun. So we use this telescope to search for the specific spectral signatures for a very specific molecule called benzonitrile, which is the C6H5CN, or it's a benzene ring with a CN molecule attached to it. And so here you can see that this is an example of the spectra we use. So each molecule gives off a very specific, emits at very specific frequencies. So this is the red is the specific predictions we have based on our model, and the white line is the data we got. So this is actually a fairly solid detection. And this was very exciting for us because this was the largest molecule ever found with radio astronomy. It was the first benzene ring containing molecule found with radio astronomy. And the fact that it was very similar to benzene for a variety of chemical reasons means it's basically a one-to-one property of if you see this molecule, we know for certain that benzene is there too. So we can use this as a way to study benzene chemistry. Now this, the reason I have to say a lot of these caveats with radio astronomy is because there's this other molecule, class of molecules, they're called buckyballs. It's one of the 3 forms of pure carbon. So diamond, graphite, and these buckyballs, where they're molecules that only contain carbon. So that's why I have to give that caveat. And in particular, this got a bit of press release, which was kind of interesting, though, as we found out, and as it was alluded to, if you look it up on the Wikipedia page, one of the first 2 sentences in there says that the molecule smells like almonds, which is kind of interesting. So if you look at the news articles, you'll see astronomers detect almond-scented molecule that helps solve interstellar radiation mystery. Cool, that's really exciting. Tech Times had a similar thing, but something like Newsweek started going on about only talking about the fact that the molecule smelled like almonds and nothing else really of importance. So we went from caring about one form of pure carbon with these buckyballs to a different type, diamonds. So anyways, so now that we found this molecule, there was a lot of interesting questions that we could continue with of are other things we can now study with aromatic chemistry in space. So are there other aromatic molecules in this cloud of the Taurus molecular cloud? And how complex do those molecules get? We can ask, how are these aromatic molecules unique to just this one source? Like, so we picked the source because we thought it was most likely to be there, but does it also appear everywhere else? Or is this just kind of this strange unicorn? And can we use it to talk about aromatics everywhere in space? And a big question is, how does this aromatic chemistry differ across different spaces in the galaxy and throughout time? So as you have a young source or an old source, or even getting to the formation of a planet, how does aromatics come into play there? So to motivate this, we, with that motivation, we set on a couple more surveys with the Green Bank telescope. And so astronomers love a good acronym. So 2 of them we got here are Gotham, GBT observations of TMC1, hunting for aromatic molecules, which was a large project, over 700 hours to study this, and Arkham, a rigorous K-band hunt for aromatic molecules to look for aromatic molecules outside of this one specific source. And so this is, we had a couple papers come out recently within the past few months of kind of our first big data release of new molecules that we found here. And a lot of these are really exciting for a variety of reasons. And so I'll highlight a few of them here. On the very left, you have C5H5CN, and this was exciting. It was the first 5-membered ring ever found in the interstellar medium. Benzonitrile, that's C6H5CN. I mentioned that already, of the first benzene-related molecule. On the top, you have the longest carbon chain ever found, which is HC11N. You have some really weird isotope substituted species. So instead of 12 carbon, you have 13 carbon in one of the positions. And that actually has a lot of interesting chemical implications. And one of the most exciting ones was we were talking about how benzene can be used to probe later these larger pods that we can't uniquely identify. Well, it turns out we can, and we actually were able to, with this survey, find C10 H7CN, and there's two different forms of it. And we found the first unique pause, which was really, really exciting among these surveys. So to answer those questions, are there other aeromalics in TMC1? Yes. And how complex? As far as we can tell, very far, in the sense that we're already finding multi-ringed species, which is very, very exciting. So the next question is, are aromatics unique to TMC1? Now, I didn't have a cool logo made for Arkham, so I just borrowed from the popular board game. And from our first release there, we found that aromatic chemistry is not unique to TMC1. In the first 4 other sources we looked at, we found them in 4 other sources. And this was from a range of a young dark cloud, which is kind of a little bit younger than this Taurus molecular cloud we looked at. We looked at sources that were just starting to get a little too heavy and start collapsing to form some sort of protostar. We found it there. We looked towards the source where the protostar was just starting to turn on, and we even saw it there. And so it's very exciting to show that aromatic chemistry is ubiquitous and seen throughout this kind of first stages of star formation. So are they unique? No. And now the final question is kind of how do aromatics differ across space and time? Well, one way you can do it is you can compare the amount of different molecules in a source. So, okay, I have molecule A and molecule B. What's the ratio of the abundance between them? And what we found here is that of our 5 sources, they belong to 2 different clouds. And the ones that belong to one cloud, all those abundance ratios seem to be similar. And if you looked in a different cloud, the Taurus cloud, for example, the abundances seem to cluster just to be related just to specific clouds. So the ones in Taurus are related and the ones in Surface. So that maybe says something's going on between the different clouds that will impact how aromatic chemistry proceeds. Another way you can do is you can compare it to theoretical models. So a lot of work has gone into simulating chemistry in space with large chemical simulations. And what we found is with the most state-of-the-art chemical models that we knew about, they did not even get close to producing enough molecules for what we see in space. So we have an abundance of riches. For every single new ringed species we saw, the models did not produce enough, which means new detections often require new chemistry, which means this has kind of just been an unexplored regime because we didn't know that they were really there. We didn't know enough about them. So this is lots of new exciting work for us to now understand better. Why are we seeing so much of these molecules that we didn't expect to see there in the first place? So stay tuned on that question. So onward and upwards, only about half of the data from the first survey was analyzed so far from these results. So we're going to have more new molecules. Only about 20% of the sources, roughly, for Arkham were analyzed, which means we're going to be able to look at a much wider range of sources to study aromatic chemistry. And the models are constantly being worked on. So we're working very hard to try to figure out how do we actually really make these molecules and how can we reproduce what we see in space. And so that's, I think, takes me right up to the time. And thank you very much.
Awesome. Thank you for coming here and giving us that talk. So if you do have any questions for our speaker, please feel free to type them into the chat and we can go ahead and ask them. So I guess one question that I have is, you're looking for these spectral signatures in infrared or radio, some kind of transitions where you get this known kind of emission peak. How do we know the wavelengths of these? Like, are we able to actually physically make these on Earth and
Yeah,
see
no, that's
them? Or okay.
That's a great question. And so a lot of the collaborators I mentioned on there, their job is they will actually go and measure the spectra of the molecules in laboratories here on Earth. So, they will take benzene in the lab or, a variety of different, molecules, kind of zap them with the laser to produce a bunch of molecules in a tank, and then kind of make it so that they will emit in the and produce spectra in the infrared or the radio, and then they will very accurately account for every single molecule that they would expect to see, and then they provide catalogs for astronomers to measure them. And so it's a very strong collaboration in astrochemistry, is having people in the laboratory, people who do these modeling sort of work, and people who actually observe in space constantly have to talk to each other to figure out what do we want to look for, what is it going to look like what does the spectra look like, and how much of it do we think will actually be there.
So are there molecules that they've created that you would have expected to find out there that you haven't seen yet?
Yeah. So if I go to, let's see if it'll let me do this. Here. So for example, this is some of the molecules we did find. One thing you'll notice is that these rings, the inner parts of the rings are always carbon. And one kind of interesting thing that are common in a lot of chemistry on Earth is sometimes you will have a different atom in the middle of that ring. They're referred to as heterocycles, where you can have something like a nitrogen in there instead. And so that's something that we would have expected to see based on what we see in the laboratory that we haven't quite seen yet in space, that we think would be interesting for us to know why it is there or why it isn't there, or if it is there, why do we see so little of it?
Okay. Also, earlier you had mentioned that you may get chased down with a truck if you have a cell
Yes.
phone at the. Have you been chased down by a truck and did you escape?
No, because I've seen the truck, but more just I saw it parked there. But no, it's actually it's a government regulated area where there's both the Green Bank telescope as well as a variety of other quantum or Air Force based institutions in the area, and it's kind of a large chunk of land that's kind of demanded by law to be radio quiet. So you can't have microwaves around, or if it is, it has to be in a Faraday cage. And so because it's a government mandate, there are people who specifically have very large parabolas on the side of a truck, and they will, if they see the signal, and they will, they can just drive down and find you there. If you get close enough to the telescope, the spark plugs in cars and the screens on digital cameras are actually can be detected by the telescope, which is pretty crazy.
Very cool. So another question, we're talking about how these elements are made. It was like in one of your early slides.
Yeah.
I know that there's now we've seen that you can make some of the elements in like neutron star collisions from the
Yes.
LIGO discovery a few years ago. Is
Yeah.
there, I guess, do we still know exactly how these elements, where exactly they are forming? Are there some that we think to have formed in supernova that are now in these neutron star collisions?
Yeah, so one thing you may see is, as you can see, a lot of here are mixed colors. And the reason that is because it's a little bit of column A, a little bit of column B. It's tough to know exactly what is dominant for each and every single element. And I think this is, it's not my exact field of study. That's much more on the kind of nuclear physics combined with looking at stars in particular. But I know it's an active field to try to really nail down what is the history of all these different elements and where do they come from. Because it tells a lot about, for example, when I go to study the chemistry, I really need to know what the initial abundances of all these different atoms are, so I know how much I'm working with. But I know it's an active field right now that people are working on. I don't know specifically about the, neutron-neutron mergers and what they make.
Okay. So we got a question here from the chat. How do PAHs impact star and planet formation?
Yeah, so that's a good question. So I mentioned, so like, for example, these PAHs often they can be important to the actual formation of dust in of themselves. And those dusts are the things that coagulate and form. And once you get enough of this material together, that's things that will actually form stars, planets, rocky bodies. In the solar system. And so in that sense, they're kind of the building blocks. In addition to that, I had mentioned this infrared emission that they give off a lot of in space. And that's also really important for star formation because it's a way to, as you're pushing and collapsing all this material down, it's heating up very rapidly. And you kind of need a way to get energy out of the system. You need a way for it to escape. And otherwise, when you get something really, really hot, a gas will want to expand. And so this is one way that energy can kind of leave the system is PAHs can vibrate back and forth without destroying themselves because, like I mentioned, they're very stable. And so by vibrating back and forth, they can emit emission in the infrared as a way to cool down gas. So those are two ways. I'm sure there's plenty of other interesting things as well, but yeah.
Cool. All right. So one last question I have is, we talk about radio observations. Some of the big ones that come to mind are like Arecibo or like the VLA.
Yeah.
So what advantage does Green Bank have over those facilities?
Yeah.
And I guess like how could VLA also kind of augment what you have observed?
Right, yeah. So Green Bank's really nice in the sense that it's a big dish. So if you're trying to look for very, very faint signals towards one place, you don't really care what the place looks like, all you get is very sensitive spectra from them, which makes it very nice for detecting molecules. Arecibo runs into an issue of the frequencies they look at are often a little low, to the point where the fingerprints of molecules are not, there's not a lot of them down at that frequency. Most of them kind of exist, kind of, I would say, above like 4 gigahertz or so. And Arecibo kind of works below then. So that's just that's a technical reason why. And for the VLA is actually really nice for studying a lot of molecules, because so the VLA is the very large array, and what arrays in radio astronomy give you is not just the ability to measure if a molecule is there, but you actually get an image out of that. So you can figure out where is a certain molecule most abundant in a source. Is it in the outer parts? Is it in the center? Is it related to, the dynamics of the source? And so that's the information that the VLA gives you. So while the Green Bank telescope is very good at very sensitive single, I just look at an area and how bright is it. And it's wonderful for doing that, detecting new molecules. The VLA gives you a lot of information about where those molecules are, or any sort of properties. The fact that it gives you an image is very powerful. And so we use it a lot. We're working on trying to study this source with the VLA right now, actually.
Okay. Awesome. Well, thank you for coming out and giving this talk to us. I don't know that we've had an astrochemistry talk before, so it's really cool to kind of branch these two sciences together.
Yeah, well, it's great. Thank you. Thank you for having me. It was a lot of fun.
All right. So next up, we are going to have our trivia session. I have the link with me here, and I'm going to paste it into the chat. So if you'd like to play along, go ahead and follow that link there in the chat. Arvin is going to come online and give you all the questions.
Yeah.
right.
Am I ready to go, Michael?
You are ready to go.
Great. Yeah, and to be clear, when we asked Andrew to give this talk, I don't think Michael knew astrochemistry was a thing. So we all learned something.
I mean, you take any science, astrobiology, astrophysics, you can combine any two sciences, right? It's how it works.
Yeah, sure, okay. Can you see my screen that I'm sharing now?
Yes.
Great. All right, so the theme for tonight's trivia is obscure astronomy. For those of you that are joining for the first time, I'll go through how this works real quick. So I'm going to ask you all a series of 15 questions through this little PowerPoint slideshow. They are themed each month, sorry. This month's theme is obscure astronomy, which means I'll be giving you astronomy terms that are either just not common knowledge or a little bit more obscure than what you would generally learn in an Astro 101 classroom. And then I'll give you two different definitions of that term. One of them is the actual definition, and the other is something that I made up this afternoon while I was procrastinating. This is, for people that are familiar with the board game Balderdash, that's kind of what this is based off of, so think of that when you're going through this. And the goal here is that you will want to pick which of those two terms is the correct definition so that you can get points. The team with the most points out of 15 will be the winner for tonight, and we have some nice prizes to send you. In the case of a tiebreaker, so if two teams tie with the highest points, then I will choose the winner based on which team I think has the best astronomy-themed name. So if you think you're doing well, try hard to come up with something nice and creative to hopefully win that tiebreaker. The link is at the bottom of this page right here. So if you click on that, or sorry, you can't click on the screen, but if you go to the link that Michael gave you in the chat, you should be able to see the questions and start to answer them. The prizes that we have are here. I don't know if we have face masks right now. We will have them next month if they aren't available yet. But we have Astronomy on Tap State College magnets, bottle openers courtesy of the Central Pennsylvania Observers, and some nice koozies. So yeah, that's what we have to give out if you win. Quick example question. So astronomers are typically really uncreative when naming things. So there's a telescope at Las Campanas Observatory called the 300mm telescope. And you would have to choose whether that describes a telescope with a 300mm aperture or a telescope that operates while submerged in 300mm of water. Hopefully most of you would guess that this is a telescope with a 300mm aperture. I don't know how well we would be able to observe anything with a telescope underwater, but we could always find out, I guess. Yeah, so following this example, just choose the more correct answer of the two for each of the next questions. Question 1, which should be the first question you see on that answer sheet, is tektite. And the two definitions I'm giving are debris formed from the ejection of terrestrial material following or during meteorite impacts, or heavily oxidized rocks discovered by the Opportunity rover on Mars. If anybody wants clarification on any of the definitions I'm giving, maybe put some questions in the chat and Michael can bother me and let me know if that's important or if there's something I need to clarify or correct. So, number 2, the Hennier-Greenstein function. Does this describe the motion of a comet as it interacts with the planet's magnetic field? Or does it describe how light scatters in planetary atmospheres and interstellar dust clouds? Number 3, Saros. So is this the period between two identical lunar or solar eclipses, or is it the change in the reflectivity of a radio telescope due to strong winds? I'm going to go through all of these a second time. So after I go through all 15, I'm just going to flip through the slides again really quick to have you guys see the answers another time. But all of these definitions are also in the answer sheet, so you can just go there to look. Number 4, Gegenschein. I'm not sure if I'm pronouncing that right. Maybe somebody that speaks German can correct me. Is this a bright spot in the sky opposite the position of the sun due to backscattering from dust? Or is it the ultraviolet brightening of interstellar gas that is backlit by a quasar? Number 5, the Encke gap. Is this the underdensity of stars and gas between the Milky Way's spiral arms? Or is it the gap inside of Saturn's A-ring carved by the moon Pan? Number 6, phonon. Is this the particle or quantum of energy associated with compression waves and vibration? Or is it the average distance traveled by a star traveled by a photon emitted by a neutron star? Number 7, epact. The number of days since the new moon at the start of the solar calendar year, or a crater left by a meteorite that impacted at a steep angle of incidence. A friend of mine that speaks German said that I pronounced Gegenschein correctly, so nice. Number 8, Mintaka. Is this the bright star on the west end of Orion's belt? So the furthest west of those 3 stars? Or is it the time interval between periods of strong volcanic activity on Jupiter's moon Io? Number 9, Lutz-Kelker bias. Does this, so this is a statistical bias, I'll give you that clue. And the two options are that it causes the measured parallaxes of stars to be systematically larger than their true values, or it can lead to the underestimation of the density of galaxies in the direction of Polaris, the North Star. Number 10, nutation. Is this the change in the relative brightness of a star due to scattered moonlight, or a periodic variation in the inclination of the axis of a rotating object? Number 11, Urca process. Is it a sequence of nuclear reactions driving the cooling of neutron stars, or the process by which oxygen combines with heavy metals to form oxides in stellar atmospheres. Number 12, I'm not sure about that one. The transitional state during which merging spiral galaxies relax to form an ellipsoid, or the extremities of the rings of Saturn as seen from the Earth. Number 13, Captain Star. Is this the brightest Cepheid variable star in the Andromeda Galaxy, or is it a nearby M-dwarf star in the galactic halo of our own galaxy? Number 14, the Van Allen belts. Are these regions of the Milky Way where stars orbit faster than their nearest neighbors? Or is it a zone of energetic particles from the sun that are captured by Earth's magnetic fields? Last but not least, number 15, the zone of avoidance. Is this the area of the sky obscured by the disk of the Milky Way galaxy? Or is it the hallway near my advisor's office where I carefully avoid when I'm not being productive? All right, I'm going to go back to number 1 and then flip through these pretty quickly. I'm only going to read the name of the term, not the entire description again this time, because hopefully all of you can read as well, and you do have the terms in the answer sheet. Number 1, tektite. Number 2 is the Henier-Greenstein function. Also, I didn't say this before, but you all have until the end of Astronomy in the News to submit your answers. So that's the next segment after this. And I will be starting to grade the answers and decide the winner as soon as Astronomy in the News ends. So I won't be accepting any answers after that, once the third talk starts. Second talk starts. Number 3, Saros. Number 4, Gegenschein. Number 5, Encke gap. Number 6, phonon. Number 7, epact. 8, Mintaka. Number 9, Lutz-Kelker bias. 10, nutation. 11, Urca process. Number 12, Onsai. 13, Captain star. 14, the Van Allen belts. And number 15, the zone of avoidance. Okay, all right, I'm going to stop sharing now and hand it back off to Michael.
Okay, I think we are ready for Astronomy in the News then, and so I'll pass this back off to Jacob.
Excellent. Hopefully you can all see this, and welcome to another edition of Astronomy in the News. So for our repeat attenders, this may look and sound familiar, though this is the Arecibo Observatory, which made our Astronomy in the News segments in August after a cable snapped, and then again last month after another cable snapped. And we reported last month that due to the concern of the increasing stress on those remaining cables, it could lead to cascading failures. And so they decided to decommission the instrument and perform a controlled dismantling. However, only a few days later, those cascading failures occurred, and the 900-ton suspended platform collapsed, which you can see here in some sad but actually really interesting videos. So we'll just watch this for just a little bit. You can see all the cable snapping, debris flying everywhere, towers crashing. So this was a very sad, sad to see. I believe the next short little video, you can see this middle wire or cable here fraying and then finally snapping, which then leads to the rest of them quickly going. And there it goes. Some cool drone footage. Yeah, pretty wild. So that's Arecibo now officially collapsed and no longer in operation. In other sad news, December 7th marked the loss of a pioneer in space and astronomy, Chuck Yeager, who was the first pilot to break the sound barrier and helped set the stage for the astronaut program, died at age 97. And so if you want to see more about this era and the beginnings of the space program, I would recommend you watch the movie The Right Stuff, which is good, and among other things has a surprise young Jeff Goldblum, which I wasn't really prepared for. And that was one of my takeaways from this movie. For the nighttime observers out there, over the next week, Jupiter and Saturn will be getting closer and closer in the sky, peaking about December 21st on the winter solstice. And this great conjunction will be your best bet if you want to grab Jupiter and Saturn together in one picture. Maybe you thought it was difficult to get your pets all lined up together each year for your family Christmas photo. Well, this will be the closest that Saturn and Jupiter have appeared in the sky in 4 centuries. So this is really a holiday miracle. Though they're maybe getting along a little better now because these solar system siblings will next be this close in about 2080. So mark your calendars for then. And then before I throw it back to Michael, I want to introduce a new and maybe one-time segment that we're calling Astronomy in the Fake News. To our dismay, Snapchat has launched a new feature called Astrology on Snapchat, where users can read up on their astrological sign, check compatibility with friends, etc. And so, so far, based on my date of birth, I've been told by this app that I am, and I quote, playful, expressive, curious, bold, enthusiastic, positive, sociable, artistic, diplomatic, caring, dedicated, sensitive, determined, brave, impulsive, proud, courageous, optimistic, imaginative, creative, giving, strategic, observant, pragmatic, intense, magnetic, and deep. So this is confirmed what I've always suspected, which is I have absolutely 0 negative traits. But yeah, I have yet to test the actual compatibility feature with friends. Either I haven't been able to figure it out or none of my friends actually have this set up yet. So I can't say how well that works. I imagine that all of them will be some variant of these 2 astrological signs can often enjoy a loyal, trusting friendship, but be wary as friendship between these 2 signs can often lead to discord and distrust. So your mileage may vary, but bottom line is don't put much stock in astrology. So I'll go ahead and pass it back to Michael so I can stop talking now and we can move on to our next speaker. But before I go, a quick reminder to turn in your trivia answers now. And this has been another Astronomy in the News with Jacob.
Thank you, Jacob. I wonder what they have to say about the Jupiter-Saturn conjunction. How does that affect your Snapchat astrology horoscope?
Yeah, who knows?
All right, let's get back to the real science then. We're going to continue on with our last talk of the night. So from Penn State, Steve Kerby, a graduate student in our program here, is going to tell us about finding aliens with gravitational lensing. Go ahead, Steve.
Thank you, Michael, for that introduction. Let me just share my screen quickly. Da-da-da. Can you see that all right?
Yep, you're good.
All right, excellent. Well, as Michael just said, I'm Steve Kerby. I'm a second-year grad student here at the Penn State Department of Astronomy and Astrophysics. And I'm particularly excited tonight to be able to tell you about some exciting new developments that have to do with gravitational lensing and applying that science to exploring the universe, both in humanity's exploration of the universe and in the search for extraterrestrial intelligence. So I'm going to start my presentation by conveying that famous Douglas Adams quote that underpins kind of this whole discussion. I won't read the whole thing, but the general gist is that space is truly titanically large. The 2 units I'm going to be bandying about in this presentation are the astronomical unit, the distance between the Earth and the Sun, at a mere 93 million miles, and the light year, which is the distance that light travels in 1 year, which is 5.8 trillion miles. These distances are unimaginably huge by human standards, and they pose a real problem when you're faced with that eternal, that quandary, how to get information from one place to another. In this kind of cartoonish diagram, imagine you're standing on the left and you have some electric power, and you have a friend some short distance to the right, only a few trillion miles, and your friend is trying to realize some information from you. You're trying to transmit information to your friend. If you have some electrical power, how do you accomplish this? Well, one way to do it is by plugging your power outlet into a light bulb. Now, a light bulb emits light in all directions. The photons stream out from a light bulb onto the entire sky. And this means that no matter where your friend is standing around you, they're bound to get some photons. But because the photons are traveling out in all directions, it also means that as your friend moves away from you, they see fewer and fewer photons. Because the flux from the light bulb goes down as distance squared, that means a friend who is 2 miles away from you will detect only 1/4 the number of photons as a friend who is 1 mile away from you. And when you're dealing with transmission across trillions and trillions of miles, that means there's a big problem if you're shining light in all directions. So what's one way we can overcome this problem of light becoming too diffuse and the power becoming too small at large distances? Well, that would be by replacing our omnidirectional light bulb with a laser pointer. Now, a laser pointer emits light in a very almost perfectly parallel beam. And that means so long as your friend is standing exactly along the line of the laser beam, it doesn't technically matter if they're 1 mile or 2 miles away from you. They will be able to detect the same amount of photons coming from your signal. However, if your friends are standing off the axis of this laser beam, like those 2 unfortunate souls at the top of the slide, they won't detect any photons because the laser beam is pointed away from them. This is a concept that in radio transmission of information is called directional gain. And it conveys how we can communicate across interstellar distances, trillions of miles. Directional gain is described by the letter, is represented by the letter G, and it roughly represents a focusing factor. If a light bulb emits its power uniformly across the entire sky, we say that it has a gain G equal to 1. As the gain increases, the fraction of the sky towards which a light source emits radiation goes down by that same amount. So a gain of 10 means that your light source is only emitting light towards 1/10 of the sky. And because the power going into that light source hasn't changed, the density of the photons in that cone go up by a factor of 10. So the gain also says how many times brighter than an omnidirectional source does your focused light source appear. As you can see on the bottom, I've got some schematic pictures showing as gain increases, the transmitted beam of photons gets narrower and narrower and narrower. So a gain of 1,000,000 means that your light source is only emitting towards 1/1,000,000th of the sky. But within that tiny slice of the sky, the light source is truly very, very bright. So instead of broadcasting our signal all across the universe, if we're trying to transmit a few trillion miles, perhaps we can make our transmission very high gain, aim it just at the target, and increase the brightness in that small target. So just to give a few examples of how this is used in the real world, one of which is particularly newsworthy, the New Horizons probe is a famous NASA probe that flew by Pluto a few years ago. Its high gain antenna, that big dish you see in the left-hand picture, has a gain of about 30,000, which means that the size of the beam, the angle on the sky towards which that information is transmitted, is about 0.7 degrees, where a degree is 1/360th of a full circle. As a dish gets larger and larger, gain also tends to increase. So rest in peace, Arecibo, one of the most famous and powerful radio transmitters and telescopes, which up until recently was a powerful tool for science, has a gain in excess of 1.5 million. And that means that the beam size, the patch on the sky illuminated when Arecibo is transmitting, is approximately 1/10 of a degree, so incredibly tightly focused. Generally, this discussion of gain and radio transmission, what I'm trying to convey is that as the gain increases, the beam of your transmission into space gets more and more focused. Inside that beam, it becomes brighter and brighter and brighter as the photons are packed into a smaller area. And generally, a higher gain means a more efficient transmission if you can keep the beam on target. So I'm just going to jump back for a moment and reconvey, I hope, just how large space is. How are the dishes, the gains that I described in the previous slide, compared to the vastness of interstellar space? Here you can see kind of a scale model of our exploration of the outer solar system. On the far left is the sun, and Neptune, the outermost planet in our solar system, orbits at approximately 30 astronomical units, 30 times the distance between the Earth and the sun. New Horizons, that famous probe I mentioned, is approximately at 50 astronomical units from the sun. And Voyager 1 and 2, our most famous interstellar craft thus far, are between 120 and 130 astronomical units to the sun. If we want to explore the nearest star system, Alpha Centauri, we need to get 270,000 astronomical units from the sun, or 4.5 light years. That means that light would take 4.5 years to get there. And this just reiterates the Douglas Adams quote I mentioned at the beginning. Space really is big. So if you want to reliably convey information from one part of the galaxy to another part, or even between the nearest stars, you very much need very focused transmissions, very high gains, and very bright light sources within those transmissions. So suppose we were to send a probe to Alpha Centauri, and we want it to send its information back home. New Horizons has a gain of 30,000, and that's impressive, but at Alpha Centauri distance, truly that might not even suffice to communicate home back to Earth. It's infeasible to send a dish the size of Arecibo to Alpha Centauri. A New Horizons, the probe past Pluto, is approximately the size of a kitchen table or a small car, perhaps. And unfocused beams, even beams with a gain of 30,000 or so, they waste too much energy. Too much of the energy you spend transmitting streams out into empty space, and only very little actually strikes the target, the receivers back home on Earth. We need some sort of lens that can focus the initial unfocused beam into a very high gain beam, a parallel beam, a laser pointer across the galaxy that conserves flux and allows us to transmit information. Now, Wile E. Coyote is not available to drop Acme giant lenses across the galaxy at our whim. But if I'm not alluding to it strongly enough, and as mentioned in the title of the talk, one way to do this is with gravitational lensing. Described in its current theory by Einstein's famous theory of general relativity, gravitational lensing is how light follows a geodesic path around massive objects, being bent towards them, as you can see in this diagram in the lower right-hand side of this page. Light from a source in the background is bent around a massive object and eventually refocuses down to an observer on the far side. It's observed in all sorts of objects throughout the universe. Famously, the sun in the 1919 solar eclipse by Lord Eddington. But it's also observed around black holes in their accretion disks and in galaxies in the faraway universe. So gravitational lensing works exactly like we want it to. It could take an initial unfocused beam and bend the photons that would otherwise be lost out into space onto a receiver across the galaxy. And this is a fairly new topic of research in astronomy. It was proposed only a few decades ago, and investigations of it for human exploratory purposes are only really taking off recently. There are two ways in which this gravitational lensing of light could be harnessed for exploration. In the first, you would place a space telescope, like the Hubble Space Telescope, 550 astronomical units from the sun. And as light from a very distant star on the far side of the sun goes past the sun's gravitational force, it would be focused down onto that space telescope. That's one way in which gravitational lensing could be harnessed for exploration. Another way would be using a radio transmitter to broadcast information towards the sun or indeed any star, then relying on the gravitational potential of that star to bend that transmission into a perfectly focused laser beam of radio waves that can stream across interstellar space and eventually be received reliably by some distant probe across the galaxy. This sounds very science fiction, but in fact, 2 mission proposals have actually suggested it could be done within our lifetimes. To use the solar gravitational lens, the telescope or the transmitter, either one, depending on what you're trying to do, needs to get out to 550 astronomical units. Now, this is obviously much, much easier to accomplish than going to 270,000 astronomical units. But still, compared to New Horizons and Voyager 1 and 2, which maybe have reached 100 astronomical units, it would still require a vast expansion of our spacecraft capabilities. But some very interesting proposals have been put out to use this technology. The first is called FOCAL, that's an acronym, which proposes sending a space telescope out to 550 astronomical units to collect light that is focused by the sun's gravitational lens. That's the first of the 2 cases I mentioned previously. The magnification and the light gathering capability of the sun's gravitational lens is so great that the surfaces of exoplanets light years away could be resolved to kilometer scale. A map of the cosmic microwave background, the afterglow of the Big Bang, could be plotted out to incredibly high precision. Alternatively, an Italian physicist named Claudio Maccone proposed building a radio bridge between the stars. Instead of just taking 2 probes, sending one to another star, pointing them at one another, and hoping that they can pick up each other's signal, Dr. Maccone suggests using the gravitational lenses of the 2 stars, the Sun and perhaps Alpha Centauri, or one of the stars in the Sirius system, to focus and then refocus the beam onto the transmitter or the receiver. So even though this technology seems fantastical and requires leaps forwards in human spacecraft technology, it may be feasible to use the gravitational lenses of the Sun and other stars to facilitate our own science. Now, I'm going to start talking now about 2 research projects that are being done here at Penn State to investigate this use of the stellar gravitational lens in a little more detail. The first is a project I'm conducting for a class I'm in, Astro 576 on SETI. I'm investigating the engineering difficulties of building and maintaining one of these stellar relays. And the main difficulty I'm finding is that unlike a picturesque idea of a star as fixed in space, stars actually jump around as reflex motions and gravitational forces tug on them. The sun, for example, you can see in the upper left-hand corner, is being dragged around by the gas giant planets, Jupiter and Saturn most notoriously. In the lower left, you can see Alpha Centauri, the 2 stars in that binary system, circling each other to a great degree. So the stars themselves, the objects we're relying on to focus our transmission, are not stable. They jiggle around on the sky. Furthermore, the spacecraft itself isn't stable. It's being pulled inwards towards the stars. And if you recall earlier, the spacecraft has to be beyond 550 astronomical units. So if the star drags it too far inward, it's no longer usable. And this is a real problem because if we want to get incredibly high gains to transmit across the galaxy with interstellar spacecraft, that means the beam is going to be very narrow, perhaps even narrower than an arc second on the entire sky. That's a 60th of a 60th of a degree on the sky. In fact, the position of the spacecraft in a telescope or transmitter arrangement needs to be maintained to within a kilometer over interstellar distances. That's 10 to the negative 8 astronomical units. So my research on this topic is focusing in on how these problems, the trembling of stars and the perturbing of spacecraft, might be dealt with. Now, the other project I'm super excited to talk about is a group effort by all the students in Astronomy 576. And you can see all their names listed here, along with Jason Wright, the instructor of that course. Professor Wright is guiding us through investigations using the Green Bank telescope, interestingly, the same telescope that was mentioned in the previous talk. Now, we're using the telescope to demonstrate a new way of searching for extraterrestrial intelligence, SETI, if you will. And that's effectively trying to look for spacecraft that are using the sun to transmit interstellar communications, if those spacecraft were placed by an extraterrestrial intelligence. So imagine for a moment that a spacefaring civilization, an extraterrestrial intelligence, has placed transmitters that use the gravitational lens of the sun all across the galaxy. And perhaps there's one around the sun, far away at 550 AU. How could we detect transmissions from that spacecraft if they were pointed towards, say, Alpha Centauri? Well, the transmission wouldn't be coming from Alpha Centauri. It'd actually be coming from opposite on the sky from Alpha Centauri. So what my collaborators and I have been working on, it's a group effort of which I only play a small part, is to use the Green Bank telescope to look opposite the sky from Alpha Centauri and see if there are transmissions being beamed towards the sun, which Earth might intercept, focused by the sun, towards a receiver at Alpha Centauri. This is an ongoing investigation, and I don't have results to share with you at the moment, but it's an exciting demonstration of how this gravitational lens technology might not only benefit humanity's exploration, but can also branch out into other fields of astronomy like SETI and might even be used by other civilizations throughout the galaxy. So to summarize just a little bit, there are three main points that I've touched on. First, gravitational lensing by any star in the galaxy can be used to greatly benefit scientific space exploration and other searches across the galaxy. First, it can focus transmissions or telescope observations by bending light from parallel beams down onto a point or from transmissions from a point into a parallel beam. My own research is showing how there's a great need to correct for perturbations on the star. As planets jiggle a star around back and forth, the spacecraft needs to correct for those motions to maintain a very precise alignment with its target. Finally, I described a SETI search that a collaboration here at Penn State is doing to see if perhaps an extraterrestrial intelligence is using the gravitational lens of the sun to transmit information across the galaxy, specifically to Alpha Centauri. So this is a young field that's still developing, and I'm excited to see where it goes, not only in the next few years, but also in the coming decades. Perhaps it can become a reality. With that, I'm happy to take all your questions. And thank you for coming to Astro on Tap. Michael, back to you.
All right, thank you, Steve. So again, if you have any questions for Steve, type them into the chat and we can go ahead and ask him while he's here. So one question I have is that you mentioned trying to look for these signals. What exactly are you looking for in data from the Green Bank telescope that would tell you this is a signal from an extraterrestrial intelligence?
Sure. So the Green Bank telescope, as Andrew mentioned, is a great radio observatory. So pointing it at the sky and selecting certain radio bands to take observations. The raw output of that is simply a dense text file of data. However, using a program called Turbo SETI, which is a SETI investigation program, it's possible to look through that data for signals that have a certain drift rate. And what a drift rate is it represents how the frequency of that signal is changing over time. For example, as the Earth rotates and moves around the sun, the Doppler shift of a distant signal would change, like a siren driving past on the street at a changing rate. So what Turbo SETI does is it combs through the data from the radio telescope and looks for specific drift rates that we ask of it. Now, because this probe is sitting stationary or approximately stationary out at 550 astronomical units, because that's where the extraterrestrial intelligence would put it to use the sun's gravitational lens, we are looking for a drift rate in the data that only has the rotation and revolution of the Earth in its frequency drift, because we expect the probe to be sitting stationary out at 550 AU.
Okay, so if it's sitting stationary and it's got like the sun that's in the middle and it's trying to beam something towards like my face right here, as the star moves though, is this thing gonna have to, isn't it gonna move off target? Like I guess I'm a little unsure of how the orbital dynamics of this whole thing would work. Like this thing is orbiting around the sun and still trying to point at some spot out in distance.
If the probe is, if a probe that may or may not exist is sitting out at 550 astronomical units, it can't actually be orbiting the sun. In that case, it would be rapidly crossing the sky. I say rapidly, over a course of thousands of years, and that would mean it would move off target. But like you mentioned, the sun itself is moving under the influence of the planets. For example, at 550 astronomical units, Jupiter causes the sun to wiggle back and forth a little bit, and that wiggle has a magnitude of about 1 arcsecond, so 1/60th of a 60th of a degree. And that means that if the beam from the spacecraft beamed towards the sun eventually gets a gain that makes it narrower than 1 arcsecond, the spacecraft needs to correct that. And what it would do was it would actually fire its thrusters to match the motion of the sun, which sounds pretty exerting, but this is over decades and decades. So the actual delta V, the velocity change cost, is very, very small.
Okay. So we got some questions here in the chat. So kind of just generally speaking, we were talking about trying to look at other planets outside the solar system. So how many exoplanets have we found? And I guess what do we know about the ones that we have found so far?
So I'm not personally an expert on exoplanet research. I know a lot of people at Penn State are doing that. Recent space missions and ground-based observations have found thousands and thousands and thousands of exoplanets and exoplanet candidates. And what exactly we know about them depends on how they were discovered. The two main ways in which exoplanets are discovered are either by seeing the light of their star go down as the planet covers up the face of the star, that's the transit method, and seeing the star wobble back and forth as the planet tugs on it, just like Jupiter tugging the sun and causing trouble for stellar relay alignments. We can view stars wobble back and forth as planets orbit them. So if we discover a planet, we characterize its orbit and its size and its mass using these techniques. If we had a solar gravitational lens telescope like the focal proposal, then that telescope would have to use that information to find exactly where on the sky the planet is expected to be and aim the telescope right there to try and find it and image its surface.
Okay. And got two good questions here. When using the gravitational lensing of the sun, how can we reduce the noise from other sources in our solar system, like the sun itself?
So the main technique, obviously, you're right. The sun is the brightest source of light in the entire solar system, and it's normally not advisable to take an optical telescope and aim it straight at the sun, especially when you're close to the sun, but even when you're 550 astronomical units away from the sun. If you're using the spacecraft to transmit at the sun or receive transmissions from the other side of the sun, that would probably be in the radio waves. And you could conduct those observations and those transmissions by choosing a part of the radio spectrum where the sun doesn't really emit much radio waves. If you're trying to use the sun as a telescope lens, like in the focal mission, I believe the proposal suggests using a device called a star shade, which is another spacecraft positioned some distance away from the telescope itself that covers up the sun just enough on the sky such that you can see the lensed light that comes around the sun down towards the telescope. But the star shade itself covers up the sun, so the great optical light coming from the sun, that huge bright amount of light, doesn't corrupt your data.
Okay. One more question here from the chat. What are your thoughts on the repeating fast radio bursts from the CHIME study and other recent repeating frequency FRBs? So fast radio bursts.
So fast radio bursts are a little far afield for me again, but I do have some tangential knowledge of them. The difficulty with fast radio bursts, up until recently, none of them have repeated. But like the question mentioned, the discovery of repeating fast radio bursts is really important because a core tenet of the scientific method is being able to repeat observations. That's how we gather more data. It's how we observe things again. It's how we test our theories. So repeating fast radio bursts are really impressive to be able to build up our knowledge of these strange bursts of radio waves from the universe. What are my thoughts on them? Again, they're still enigmatic right now. I believe there were some studies that were trying to link fast radio bursts to outbursts from certain types of neutron stars, but that is still very much hypothetical. It's a hypothesis to try and explain these observations, but more data and more observations are needed to be able to really pin those down. There was a lot of excitement about fast radio bursts being possible SETI signals. My personal bias is I do not think that's the case. But obviously more time and observations will possibly shed more light on what their source is.
Okay. And I guess the last question, of course, anytime someone talks about SETI or aliens, always got to ask, Steve, have we found aliens yet?
Besides all the weird stuff that lives down here on Earth, you seen those creepy crawly things at the bottom of the ocean? I think the Earth is interesting enough to keep us scientists busy for hundreds of years. No, we have not found
That's
aliens.
not it. Okay, there we go. All right. Thank you, Steve. Thank you for coming out and doing this
Thank you
talk.
for
We
having
really
me.
appreciate it. All right. Next up, we are going to go over to Arvind, who's going to give us answers for trivia and announce the trivia winner. So go ahead, Arvind.
All right, sorry, Michael, hold on. Okay, so thank you to everybody that submitted answers. Most people did actually pretty well, which I don't know if it attests to people knowing all these obscure terms or just guessing very well on the multiple choice. But yeah, so let's go through the answers right now. This is the example, which you already know the answer to. Hold on. Number one, a tektite. So a tektite is actually the debris from a meteorite impact. I learned about this in one of my geoscience classes this semester, actually. Number two, the Hennier-Greenstein function. It describes how light scatters in planetary atmospheres and interstellar dust clouds. The mathematical function here actually can describe other things as well. This is just where it's commonly used in astronomy, but it definitely does not describe cometary motions when they interact with magnetic fields. Number three, Saros. This describes the period between two identical lunar or solar eclipses. So this isn't necessarily the period between two consecutive lunar or solar eclipses. It's just when the Earth, Moon, and Sun line up in the exact same alignment again, which can take, 2 or 3 eclipses to happen. But it's something like, well, not 2 or 3, many, but it's something like 10 years that the cycle is. Number 4, Gegenschein. This is the bright spot in the sky opposite the position of the sun due to backscattering from dust, specifically interplanetary dust. Number 5, the Encke gap. This is the gap in Saturn's A ring carved by one of Saturn's moons. I don't know if there's a specific word or term for those underdensities between the Milky Way's spiral arms, but maybe there is. Number 6, the phonon. I think every single person got this one correct, which is pretty impressive. It's pretty much the sound wave equivalent of a photon. It's the particle or unit of energy associated with compression or density waves. Number 7, EPACT. I thought I was getting clever with my crater definition there, but no, this is just the number of days since the new moon at the start of the solar calendar year. Not incredibly useful in astronomy, but I guess it's a good one to know. I'm not sure if it's possible to tell exactly what the angle of incidence of a meteorite is just based on the shape of the crater, because all of them leave circular craters. Number 8, Mintaka. I was actually surprised by how few people got this one right, because it's one of the, I thought, most well-known named stars in the sky. It is a bright star in Orion's belt, but maybe that is evidence of the fact that astronomers really don't know too much about stars and constellations. They do other things a lot better. Maybe astrophotographers would have known this one more than astronomers. Number 9, Lutz-Kelker bias. This is a statistical bias that causes measured parallaxes to be systematically larger than their true values, and it has to be accounted for when measuring stellar distances and luminosities. Number 10, nutation. This is the periodic variation in the inclination of the axis of a rotating object. The Earth's axis, for example, exhibits nutation where it will change its inclination over long periods of time. Number 11, the Urca process. This is a sequence of nuclear reactions in neutron stars that cools them as they form. Number 12, Onsei. These are the extremities or the ends of the rings of Saturn as seen from the Earth. I don't know if that transitional state for merging galaxies has a name. We generally just call them irregular or merging galaxies. Number 13, Captain star. This is actually it's the closest M-dwarf star to our sun in the Milky Way's galactic halo, so the closest star outside of the disk. There is a very famous Cepheid variable in the Andromeda galaxy. It was the one discovered by Hubble that was the first very clear evidence that Andromeda was a separate galaxy from the Milky Way, but I don't think that star has a special or unique name. Number 14, the Van Allen belts. These are, again, I think most people got this right. These are the zones of energetic particles that are captured and trapped by the Earth's magnetic fields after they're coming in from the solar wind. Number 15, the zone of avoidance. I appreciate everybody that answered the second one here. The correct answer, of course, is that it's the area of sky obscured by the disk of the Milky Way galaxy. It's really hard for us to observe things that are behind the disk because the density of stars and gas and dust is very high there. You can't really see galaxies and things that are behind that. But yeah, I gave everybody credit for this answer no matter what they gave, just because, you know, they're both correct. The winner was the team with the name Darker Matter. They got a perfect score. They did get number 15 like actually correct as well, so that didn't influence whether or not they won. And yeah, I will contact you sometime later this week to let you know how we'll try and get you your prizes. Thank you everybody for playing.
All right, thank you, Arvin. And thank you again to all of our speakers and Jacob as well. There he is. So thank you for coming out. Our 7th virtual astronomy on tap. We will be back in January. We don't have a date yet, but it's going to be probably mid to later half of January. And we already have our speakers picked up. So we're going to have Milena Rice from Yale University talking about Planet 9, as well as Professor Stephen Moss and Richard Paul, who wrote a book called We Could Not Fail. It is a book about a story of African Americans in the early days of NASA and how they worked during the civil rights movement. So you have some homework for Next Astronomy on Tap. Go read that book, We Could Not Fail, and you can talk to the authors themselves in January. So one last thank you to everyone for coming out. I think that's all that I have to say. We're on YouTube, we're on Twitter, we're on Facebook. You can find us there for more details for our next event. Thank you everyone for coming out.